The pain hits you before you even fully understand what happened. Something the size of a refrigerator, moving at 30 miles per hour, has just driven a horn the length of a kitchen knife directly into your left side. You didn't see it coming. You heard it. A low, thunderous grunt. The vibration in the ground through your bare feet. And then impact. The kind of impact that doesn't sound like a movie punch. It sounds wet. And then the world tilts sideways. And you're looking at the sky, and you don't know if your ribs are cracked or completely caved in. And honestly, from the amount of fire burning through your torso right now, it could be either. Welcome to the Upper Paleolithic. Approximately 40,000 years ago, Western Europe. And the thing that just gored you is a woolly rhinoceros, Colodonta antiquitatis, a creature weighing north of 3,000 pounds, covered in thick, matted fur, and armed with a front horn that could reach 5 feet in length. You're a Homo sapiens hunter. You are fast. You are smart. You have a flint-tipped spear, and you are, right now, lying on frozen ground wondering if your lungs are filling with blood. Here's the part that absolutely wrecks me every time I think about it. They kept doing it. After this, they got up, they went back. They hunted this thing again. Thousands of times across hundreds of generations, across every continent where megafauna still walked. Not because they were stupid, but because they had no choice. The meat was too valuable. The fat was winter survival itself. And at some point, some specific, impossible to date exactly, genuinely remarkable moment in human history, they stopped going in naked. They figured out how to build armor. Not the metal stuff you're picturing. Something older, weirder, and in its own way far more ingenious than anything a blacksmith ever made. And the science behind how they did it is almost too good to be real. So let's talk about it. Because the story of the first human body armor isn't a military history. It's a forensic puzzle. And the evidence starts, as it so often does, with broken bones. In 1995, physical anthropologists Thomas Berger and Eric Trinkhaus of Washington University published a study that quietly changed how we think about Neanderthal and early modern human life. They had done what any reasonable scientist would do. They compared skeletal trauma patterns across populations. And what they found was striking. The distribution of injuries in Neanderthal remains the cracked skulls, the shattered clavicles, the compressed vertebrae, was statistically similar to one very specific modern group. Not soldiers, not athletes, not construction workers. Rodeo riders. Professional rodeo riders who routinely get launched off large, dangerous animals at high speed. The injury pattern is called high-velocity blunt force trauma, and it means one thing. These people were getting hit by animals. Repeatedly. Badly. And surviving. I want you to sit with that for a second. These aren't injuries from falls off cliffs. They're not the kind of fractures you get chopping firewood. The pattern, concentrated in the head, neck, and upper body, is exactly what you'd see if a person was taking full-body impacts from something with mass and momentum. Something charging, something swinging a horn, something with a paw the size of a dinner plate. And yet they survived. Multiple injuries per individual. Skulls that show evidence of crushing impacts followed by healing. Ribs that fractured and then knitted back together while the person kept living. Shanidar I, the famous Neanderthal discovered in Iraqi Kurdistan, had survived a blow to the head that likely cost him his left eye. A shattered arm so severe the limb may have been partially amputated, and multiple fractured foot bones. He was somewhere between 35 and 45 years old at death, ancient by Paleolithic standards, and the healed nature of those injuries means he walked around, functioned, and contributed to his group for years after sustaining damage that would have killed most people today without immediate hospital intervention. Now, the question that nobody asks loudly enough is, how? How do you take a crushing impact to the skull and not die? How does a horn strike your chest and you walk away from it? Modern trauma medicine has very clear data on what blunt force does to an unprotected human body. It's not gentle. The skull is remarkably tough, but it has limits. Unprotected ribs fracture at forces that a woolly rhino delivers routinely, with a toss of its head. A penetrating horn wound to the thorax without intervention is typically fatal within minutes to hours. Something was absorbing some of that force. Something was distributing the impact. And we know from archaeology, from experimental evidence, from basic materials science, exactly what that something was. Hide. But not just hide. Hide engineered in a way that took genuine systematic knowledge to produce. Let's talk about what we actually know about prehistoric leather, because this is where it gets genuinely extraordinary. At Contrabandier's cave in Morocco, archaeologists excavating Middle Stone Age deposits found 62 bone tools, carefully shaped, polished with specific wear patterns, dating to between 90,000 and 120,000 years ago. These tools are not spear points. They're not knives. The use wear on them, the micro scratches, the polishing direction, matches almost exactly the bone tools that traditional cultures in Africa and North America still use today for one specific purpose: scraping and working animal hides into leather. Alongside those tools were the remains of small carnivores, wildcats, golden jackals, sand foxes, with cut marks that aren't butchery marks. They're skinning marks. Cuts positioned to remove the pelt intact, preserving the fur and hide. These people weren't eating wildcats, they were harvesting their skins. Over 90,000 years before anyone thought to build a wall or plant a field, humans were running a sophisticated hide processing operation. And the key technology, the one that turns a stiff, rotting, brittle animal skin into something genuinely functional, is smoke. Specifically, the controlled smoking of prepared hide over a low fire. Smoke carries aldehydes, particularly formaldehyde, which penetrate the collagen structure of the skin and chemically bond with the protein fibers. What that bonding does is prevent the fibers from stiffening and clumping when the hide dries. The result is leather that stays supple, resists water, resists microbial rot. Leather you can fold, stitch, wear, and re-wet without it turning into a rigid board or dissolving into rot. Smoke-tanned leather doesn't just survive moisture. It maintains its structural integrity through repeated wet-dry cycles, which, if you're living in Ice Age Europe, where freezing rain and snow are the standard operating environment approximately 9 months of the year, matters enormously. I live somewhere with reliable internet and central heating, and I still complain when it drizzles. These people were waterproofing their body armor in a cave, with a fire. I respect that immensely. Now here's where the engineering gets interesting. A single layer of properly smoke-tanned hide from a large animal, a mammoth, a bison, a woolly rhino, can be remarkably thick. We're talking up to a centimeter or more of densely compacted collagen fiber. By itself, it's not going to stop a full charging impact. But the mechanical principle of layered materials distributing impact force is not modern physics. It's physics, full stop. It works the same way now as it did 40,000 years ago. Multiple layers of thick, smoke-cured hide, especially if those layers are lashed tightly together with sinew or rawhide strips so they can't simply slide apart under impact, create a composite material that behaves fundamentally differently from any single layer. The outermost layer takes the initial impact and begins to spread the force laterally. The next layer takes what gets through and spreads it further. By the time the energy has passed through 3 or 4 tightly bound sheets of treated hide, it's diffuse enough that instead of shattering a rib, it bruises the tissue underneath. Still painful, still very much not a good Tuesday, but survivable. Think of it this way. Your standard car door is not made of particularly strong materials, but it's layered, it's composite, and it will stop things that the individual materials couldn't stop alone. These hunters figured out the same principle. Not through an engineering degree, but through a brutal empirical feedback loop. Try this. Get hurt less. Try this combination. Get hurt less again. Repeat for 10,000 years. And the hide wasn't the only component. Here's the part that keeps me up at night. The bone and ivory elements. Ivory, thus specifically mammoth ivory, is not what most people imagine when they picture tusks. It's structurally complex. It has a laminated internal structure that makes it resistant to splitting under load. And in the Gravettian culture, Flourishing across Europe between roughly 33,000 and 26,000 years ago, worked ivory objects were everywhere. Beads, figurines, rods, points. These people were processing ivory constantly, and they understood its properties intimately. They knew it was hard. They knew it was tough. They knew you could shape it into long, flat plates with the right stone tools and enough patience. Archaeological sites across Moravia, Russia, and France show perforated ivory pieces, flat, worked, with holes clearly drilled or punched through them, that don't fit neatly into any ornamental or weapon category. Some are the right size and shape to lie flat against a surface. Some have wear patterns consistent with repeated contact with cordage. The academic debate about their exact function is ongoing. The materials science, though, is not complicated. A flat plate of dense ivory lashed over the ribs on the outside of a hide vest, over the specific anatomical region a horn tip most commonly strikes during a charge, would intercept a penetrating wound and redirect the force. Not eliminate it, redirect it. Change a perforation into a bruise, and the rib zone is exactly where it matters most. A punctured lung is slow death in the middle of a frozen steppe with no surgeon within 10,000 years of your position. A cracked rib is survivable. 3 cracked ribs is survivable. You walk funny for a few months and then you go back out. The difference between those outcomes, when a 2-ton animal with a spear-length horn is closing the distance fast, is often measured in centimeters of material between your skin and the horn tip. I want to be clear about what this is and what this isn't. We don't have a preserved 40,000-year-old vest sitting in a museum case with a label that says Paleolithic ballistic armor. Organic materials almost never survive that long under ordinary conditions. We have the tools that made such materials. We have the processed remains of the animals that provided them. We have experimental archaeology confirming that these techniques produce exactly the structural properties you'd need. And we have the healed skeletal trauma of the people who wore what those materials produced. The bones are the receipts. Shanidar 1 survived a crushing head impact. Multiple early modern human skeletons show rib fractures, not penetrating wounds, fractures, from high-force blunt impacts. The geometry of damage matters here. A fractured rib from a blunt strike is exactly what you'd expect when a horn impact is stopped by layered hide, but still delivers enough force to crack the underlying bone. A horn that goes all the way through, bone actually speared, is what you get when nothing is in the way. The archaeological record has far more of the former than the latter as a cause of visible skeletal damage. That asymmetry is telling you something. And here's the thing about these hunters that completely recalibrates how I think about ancient intelligence. They weren't just solving the armor problem in isolation, they were solving it as one component of an entire integrated system of megafauna hunting that required coordination, planning, and technological refinement passed down across generations. The thrusting spears they used, heavy, short, stone-tipped, were not designed for distance. They were designed for the moment of physical contact, maximum force delivered through a specific anatomical target. The problem with that approach is self-evident. Close range means the animal can also reach you. The solution to that problem is armor, and the solution to the armor problem is materials science. And the materials science solution is smoke-cured layered hide with rigid plate reinforcement over the vital zones. This is not random. This is a system. Different problem from a different angle, but the same underlying logical structure as every complex technological solution we've ever built. The same reasoning chain that eventually gives you the Kevlar vest starts right here, in a cave, with someone scraping smoke into mammoth hide with a bone tool while her ribs are probably still healing from last month's hunt. Let me give you a comparison that I think actually lands. A woolly rhinoceros in full charge delivers an impact force in the range of several tons per square meter, concentrated at the horn tip. A modern police riot shield, a thin sheet of polycarbonate plastic, deflects thrown bricks, and withstands repeated baton strikes. The material properties of well-processed, multi-layered animal hide are not equivalent to polycarbonate. But they're not nothing. Experimental reconstructions of layered hide armor, based on techniques documented in indigenous cultures that preserved these methods into the modern era, demonstrate meaningful force reduction, enough to shift the outcome from fatal to survivable under the right impact conditions. They kept refining it. That's the part I find almost philosophically disorienting. This was not a one-time invention. It was an iterative process across generations of people who never met each other, spread across 2 continents, all independently converging on the same category of solution because the problem was identical everywhere megafauna existed. Thick, layered, rigid inserts over the vulnerable zones, tied close to the body so it moves with you instead of twisting against you when the animal hits. The first body armor on Earth wasn't bronze, it wasn't iron, it was smoke and sinew and bone. Built by people who could not afford to get the experiment wrong, because the testing environment was a charging 2-ton animal with a 5-foot horn and absolutely no interest in product feedback. We live in a world where we wear seat belts to drive to the grocery store. We have helmets for cycling, pads for skateboarding, body armor for law enforcement, soldiers, and combat sports athletes. We have spent colossal resources across every civilization in human history on the fundamental problem of how to keep a soft, vulnerable body intact while doing dangerous things. And the very first people who solved that problem, the absolute origin point of that entire intellectual tradition, were hunters standing in the snow 40,000 years ago, looking at the damage done to their dead comrades and thinking, there has to be a better way to go in. They didn't have chemistry. They didn't have materials engineering. They didn't have peer-reviewed journals or safety regulations or OSHA. They had empirical observation, iterative trial and error, and a survival pressure so immediate and so brutal that failure meant not just their own death, but the death of everyone who depended on them for food through winter. They solved it anyway, with smoke and bone and time. That's the thing about our species that I think we almost systematically underestimate. We treat ancient humans like they were a rougher, dumber draft of us, a prototype that hadn't figured things out yet. And then you look at the fracture patterns, you look at the tools, you look at the physics of what they built, and the conclusion is unavoidable. They were running the same cognitive hardware. They were solving engineering problems we haven't had to solve because we live in a world where they already did. The Kevlar vest is not a modern invention dressed up in new materials. It's the oldest invention on Earth, dressed up in new materials. Next time you're annoyed, your phone case cracked, and I say this as someone who has genuinely been annoyed by this, just remember that the original armor engineers were doing their product testing against woolly rhinoceroses in the snow, without anesthesia for when the prototype failed. That reality check does something to your perspective, or at least it should. If this kind of thing rattles around in your head the way it does in mine, I want to hear about it. Drop it in the comments. Tell me which piece of ancient technology genuinely breaks your brain. Which one makes you feel like we've been arrogant about our own originality? I read those. And if you're not subscribed yet, you're going to want to fix that. Because where we're going next is going to make this one feel like a warm-up.